This is problem number 70 in chapter 7. The problem reads, a bullet is fired vertically into a 1.4 kilogram block of wood at rest directly above it. The bullet has a mass of 29 grams and a speed of 510 meters per second. How high will the block rise after the bullet comes embedded in it? So I've made a quick sketch here. We can see that this bullet is going to be fired kind of from underneath the block. The action is the bullet embeds itself in the block, and then both the bullet and the block move upwards after they combine to some final position up here. This would be our maximum height. So effectively, they will end together at some maximum height. And it's really this distance that we're looking for. We want to know the distance between where it started and where it ended. And so I basically am looking for that height. So you can solve this in a couple of different ways, but dealing with the conservation of momentum is a must at the beginning. Once you know after it's been impacted in this inelastic collision, once you know how fast it's going, you could solve it if you wanted to using conservation of energy techniques. I'm going to use kinematics. I think that's the easiest way. So I'm going to start this problem by kind of solving it in two parts. Part number one is going to be dealing with the inelastic collision. And so I'll basically start it with my conservation of momentum statement, which is basically collision. There's an extra I in there that I'll just ignore. The sum of all of the different momenta in the system before the collision must be equal to the sum of all the different momenta in the collision after in the system after the collision. Sorry. So I've got the momentum of the bullet, which I'll call P sub small b, and the momentum of the block, which I'll call P sub capital B. And of course, these are the two objects in my system after the collision as well. So I'll simply rewrite them with the prime to denote after the collision. At this point, I should see that the momentum of the block before the collision is 0. It's at rest. And so I'm going to be left with the mass of the bullet times the velocity of the bullet is equal to the mass of the bullet times the velocity of the combined bullet block system after the collision plus the momentum of the block times the velocity of the block after the collision. Again, that's combined. So finally, I'll divide both sides by, I could factor out v prime. We've seen that a bunch of times, so I'll kind of like consolidate that step, and I'll be left with mb/vb divided by the total mass, the mass of the bullet, plus the mass of the block together. Plugging some numbers into this now, I'm ready to substitute. The mass of the bullet is 29 grams, or 0.029 kilograms. And I'm going to multiply that by the velocity of the bullet, which is given to me in the problem as 510 meters per second. I'm going to divide all of that by the sum of the mass of the block. The mass of the block is 1.4 kilograms plus the mass of the bullet, so it's going to be 1.429 kilograms. When I do that, I get an answer for the combined velocity. It's going to be 10.35 meters per second. So now I know how fast these two guys are moving the instant after the collision. If I wanted to, I could do conservation of energy. I could say, hey, look, at this point here, I have just after the collision, I have kinetic energy. And at this point here, I have gravitational potential energy. That's certainly one option. I'm going to choose to do it in a separate way. I'm simply going to use kinematics. And I know that regardless of the mass of these objects, I can use the third equation and say that V final squared is equal to V initial squared plus 2a times delta y. Of course, these are y velocities here. So this equation works out recognizing that my final velocity, when it reaches its maximum height, is going to be equal to 0. My initial velocity here I just found in the collision problem. And the acceleration for something that's in free fall is negative 9.8. And so I'm looking for delta y. I'll rearrange that equation for delta y, and I get negative v initial in the y direction squared, and I'm going to be dividing that by my acceleration, and I'm also going to be dividing it by 2, right? Because I have to deal with this guy, and that's going to be equal to delta y. So now I have my expression that's going to answer this question, what delta y is. I'm ready to substitute my numbers in, and I'm going to get negative 10.35 meters per second squared divided by my acceleration, which is going to be negative 9.8 meters per second squared. Remember that this is a generic equation that's not exclusively for use in gravitation. So we have to say, hey, the acceleration is a downward negative 9.8. If this is a g here, then we don't do that by convention, but it's not. So we have to put that negative sign in there. Clearly, we see that the negative here in the numerator will cancel out with the negative in the denominator and give me a positive delta y. When I run that through my calculator, I get 5.47. 5.47 meters is equal to my height.